where you can assume that the deltas are 0. I mean, there may be no real unit in your data set where these where exactly the deltas are both 0 simultaneously. So we're going back to this model with a cross-level interaction, and where previously we got rid of all of the error terms because we averaged both over I and j. We now average only over I, and we end up getting a predicted value that is now equal to the fixed portion, plus importantly also these two error components at the end. This captures, this is the empirical base estimate for the intercept. This is the empirical base estimate for the slope, and that gets multiplied times the value predicted. And you can then graph these predictions. You can graph these regression lines, which is really what that essentially is, for all of the level 2 units that you have in your analysis. Here is basically the syntax in Stata that will get you there. The first part we already did. This is just the estimation of the random slope, random intercept model. And those first two lines. And then the action starts after that. So on the third line here, what we obtain are the fitted values. And these fitted values, those are these values here. So we use a predict command, and then we give it a name. I gave it here field hat, because any name is possible. And then in the options, that is the part after the comma, you specify fitted. And that gives you the fitted values, these values. And then for the depiction, I just sorted the data by state and by black, and then I did a two-way plot, and then you get these in the regression lines. Where actually I did one thing that to preclude some weird results. There were some states where there is no variance on race. Every one of the analysis was white. There were no black respondents. Well, in those cases, you get into this weird situation that you would get a vertical line here depicted because this is white, and all the white respondents are not black respondents. And so I dropped those cases. Now, this is, I don't know how useful it is to include a picture like this in a paper. With 33 units, or actually it's more like 29 once I drop these cases, you can still sort of make out something. What I would put in a paper as sort of a exploration of the random effects is something like this, where you can really say, okay, how does this effect of race vary across the states? That, I think, is a more useful picture, especially if you also have a picture like that for the intercepts. Then that helps. but what is a more important point is that I do think it is very useful to do this kind of interpretation. I see that way too little in political science. People sort of seem to not care about these random effects, but part of why we do this whole thing is that this is something that is of interest to us. This is ultimately what is going to show us the causal heterogeneity. This is a special case of causal heterogeneity in the sense that the slopes always remain positive. You don't get reversals of the sign of the slope. But that could happen as well, depending on the application. On interpretation, there's one more topic I want to briefly discuss. I myself don't actually know what to do with this so well, in the sense that I know what I do, which is I hardly ever center things, but there are huge debates in the literature about centering. And there are also misunderstandings about what centering does. Centering doesn't magically make things, problems like collinearity disappear. Centering helps though with the interpretation. And that is particularly important for intercept terms. And it is actually also widely acknowledged in the literature that it's more important to center the level 1 covariance than the level 2 covariance. You could center both, but most of what I've seen is that people center level 1 covariance. Now, there are at least 3 different approaches you could take to centering. One, you could say, I don't center at all. That's usually what I do, but again, there are different tastes on this in the literature, in which case we just stick with the original variable. If we decide to center, then we have 2 options. We can center around the grand mean. That is, we take the mean of the predictor over all level 1 and level 2 units, just like I sort of calculated the grand mean of y here. You can do that for the predictors as well. And you subtract that from each value of x that you observe. So you create mean deviation scores, but the deviation scores relative to the grand mean. So what you're doing is you sort of say, okay, where does some unit I in context A value x stand relative to the mean of the predictor across all individuals in all contexts? That's one way to do it. Or what people sometimes prefer is to say, well, it makes more sense to center about the group mean. You calculate the mean of the predictor in the group. That's what this x bar dot j is. And then you look in this particular group, where does the individual stand relative to the group mean? Is the score bigger than the mean, less than the mean, how much bigger, how much less? And this can help in interpretation, and I'll show you this for a particular model, which is the random effects analysis of covariance model, or what I actually mentioned earlier, the random slope and random intercept model. And here's a case where we did not center. So this variable xij is there in its original form. And here's now a little bit why centering might be a useful strategy. Because if we want to move this up to a prediction at the level of the context, so we aggregate over all the level 1 units in the context, we get an expression for a group mean that's equal to beta 0j plus beta 1j times the group mean x bar dot j of the predictor. Now, when we want to interpret this beta 0j, then what we have to essentially do is to say, well, beta 0j is the value of the mean of y that I would expect when x bar dot j is 0. So when this is 0, this second term disappears. That would be the interpretation of beta 0j, is that it's the mean of y, given that the group mean is 0. But that group mean of 0 may never occur. In fact, it's unlikely to occur. And therefore, the interpretation of the intercept is a little bit questionable. If there is really never a situation where x bar dot j is 0, then this is really not easily interpreted. And that's really the whole reason, the whole point why we end up centering, is that we can actually interpret the intercept. So here's an example where we center around the grand mean. So same model as I had here, but instead of having xij as the predictor, I now have xij minus the grand mean of x, and I introduce that as the predictor. Now, that's actually the usual way the analysis of covariance model is formulated. And with this formulation, when we aggregate over I, we get a situation where the predicted mean in group J is equal to beta 0j plus beta 1j times x bar dot j minus the grand mean. And we can now interpret this beta 0j as the difference between the observed, the group mean and the mean implied by the value of x, the mean of x in this case. This is called the adjusted mean of y. And that can always be interpreted for the simple reason that that this expression can always be evaluated. And it gets even simpler when we do centering around the group mean. So the same model again, but now we have x sub ij minus x bar dot j. So we're subtracting out the group mean. Now we aggregate over I. We can end up getting mu sub j is beta 0j plus beta 1j times x bar dot j minus x bar dot j. That of course drops out. So beta 0j in this case is the group mean of the dependent variable. So it's a very straightforward interpretation. And that's really the payoff from centering. Now, like I said, I don't do this very much. Not because I have very good reasons not to do it, but because I think I can also make sense of results without doing the centering. So I think this is more a matter of your own taste, what you think is useful, than that there is really a abiding reason to center or not to center. There's a big debate about this in the literature though, and there have been at least 3 papers that I'm aware of that have discussed this topic in great length. I think the bottom line is, if it helps you with interpretation, do it. If it doesn't help you, leave it alone.
But one of the arguments that people used for centering was that the significance, the level of significance for the cross-level interaction coefficient might be different, and that's...
Yes. Well, the argument that this goes back to a... there's actually some controversy about this. It's the same argument that people use in terms of interactions, normal interactions in the regression model. So one of the problems with interaction terms in regression analysis is that the interaction variable itself is oftentimes highly correlated with the ingredients. So if you have x1 and x2 and you interact them, then the interaction is highly correlated with x1 and possibly also x2. And that's a problem of collinearity, and what we know about collinearity is that it inflates standard errors. They're not as low as they could be, and therefore there is a suggestion in the literature that if you center the interaction comes out more significant. And that's an argument. It's one of the central arguments in a book about multiple regression by Leona, Aiken, and West. It's a book from the early 90s that makes this argument. The political science literature that talks about interaction effects takes a very skeptical view of this. It says, how can it be that centering would magically make your problems go away because you're not adding any new information. You're not adding new data, you're not adding more observation points. In fact, it turns out that yes, your interaction term may look better, but the main effects are now ending up having some problems. So you're shifting the collinearity issue in a sense. And that's why I think the argument has to be that you're better. I think when everything is said and done, it's probably more about interpretation than about that significance issue. Because you're not magically adding information. And there's a long discussion on that point in Bob Francesi and I forget the second author have a whole book on interactions where they actually make this point repeatedly that no, it's not that way. You're not adding information, so problems don't magically disappear. So on to the, not the last topic, because then I have a whole bunch of caveats I want to talk about. But we need to say something first about hypothesis testing, and I promised you that I would say something about R-squareds. Since I said it in the notes and then left it out. I will actually, and I made some changes to the notes already. I'll add a section on the R-squareds as well, and then send it to Fiona again. But let's talk about hypothesis testing first. There basically are two sets of hypotheses that we really care about. Hypotheses about the fixed effects, because those are really about the substantive predictors we're interested in. And then hypotheses about the variance components, because these are really things that help us determine whether we need the multi-level model or whether we can say either right from the start or after we've introduced the level 2 covariance, now we've gotten rid of the clustering problem. Now, hypothesis testing for the fixed effects is very straightforward, because what turns out to be one of the nicer properties of maximum likelihood estimation is that maximum likelihood estimators are asymptotically normally distributed. So we have the sampling distribution of the estimators, and that means we also have the sampling distribution of the test statistics. The typical null hypothesis is that some fixed effect is equal to 0 in the population. That usually means things like this substantive predictor really has no effect. And the test statistic we can compute is to basically take the estimate of that fixed effect over its standard error, and that test statistic we can refer to a standard normal distribution to obtain a p-value. And that works reasonably well. There is some discussion in the literature about this. What exactly the distribution is, because as often is the case, asymptotic means what? In multi-level models, the problem is we have two kinds of asymptotics potentially to deal with. One is the asymptotics in terms of the number of individuals in our data, and they're the asymptotics usually hold because we typically have lots of data points. But then when we test something that is an effect of a level 2 covariate, then the asymptotics are in terms of the level 2 units, and there we usually have not nearly as many. And it's not clear that we can invoke an asymptotic distribution. Stata seems to take a very liberal view and just does this. This is what it does. It says ratio of the estimate over the standard error that's standard normally distributed, and I'm going to calculate the p-value on that basis. There is some debate in the literature as to whether that's the best approach. So in a book by Brick and Raubenbush on multi-level analysis, they say now you should not invoke the standard normal, you should invoke the student's t-distribution with degrees of freedom that are equal to j minus p minus 1. Number of level 2 units minus the number of level 1 predictors minus 1. I think that's fairly conservative. And I don't see many people doing that. But if you use their program, they've written one called HLM, that's what they will do. And then if you use SAS or SPSS, they will actually calculate these degrees of freedom of the t-distribution very accurately using the Satterthwaite formula. And that means you can get fractional numbers of degrees of freedom depending on how much clustering there is. And that can then also give you a better approximation, better p-values. But again, it's data. The idea is simply to use this, and that may be a little bit too optimistic in terms of p-values, but probably not that optimistic, because the t-distribution converges to a standard normal distribution very quickly. So I mean, even if your j is say 30 or 40, you're probably already pretty close to standard normal. Now, on the variance components, the testing is a little bit more complicated. Here, the typical null hypothesis is that a particular variance component is 0. And you probably want to evaluate that using the likelihood ratio test, sometimes also known as a deviance test, where basically your strategy is this. You estimate the model with the variance component, and then you estimate one without. And then you compare the fit of those two models. Now, you do that on the basis of deviance. And deviance is equal to -2 times the log likelihood. So, one of the things that you will see when Stata is done with its iterations, it will give you the log likelihood. And that log likelihood, when you multiply it by -2, is known as the deviance, and you can think of that as a measure of the lack of fit. Because in theory, an optimally fitting model would have a log likelihood of 0. And so the further you're away from that, the worse your model fits. But it is usually not very helpful to report these deviances because by themselves they don't really mean much. But what is helpful is to take the deviance of two models because then you can turn that into a test statistic. And so here is what a deviance test would do. We estimate two models, I'll call them MU and MR. U stands for unrestricted and R stands for restricted. So MR here is a subset of MU in the sense that I put some restrictions on the parameters in MU to obtain MR. In particular, what I'm going to do is I'm going to actually impose some restrictions on the variance components. So in MU, I estimate these variance components, and in MR, I'm going to set them equal to 0. And now you obtain both of these models and obtain their deviances. And if the restrictions are valid, remember the deviance is a measure of the lack of fit, then the lack of fit of these two models should be approximately equal. They should both fit the data equally well, or if you want to be a pessimist about it, they should both be equally bad in terms of fitting the data. So dr and du should be roughly the same. And if the restrictions are not valid, then the deviance on the restricted model should be bigger, the fit should be worse than the deviance on the unrestricted model. Now to turn that into a test statistic, we just take the difference between those two, dr minus du, and asymptotically that follows a chi-square distribution, where the degrees of freedom of the chi-square distribution are the same as the number of restrictions that I have imposed. So the null hypothesis is some variance component is 0. We estimate a model that contains the variance and the covariance components. Then we estimate a second model that imposes the restrictions implied by the null hypothesis. And then we compute the deviance test statistic and its p-value. Now, Stata actually does something like this for us. So, if we go back to Stata in the xtmixed command, then what it tells us here at the bottom is LR test versus linear regression. And this LR test versus linear regression basically says, in a linear regression model, we don't have these two variance components. We set them to 0. The only thing that we have left is the variance of the residual, which is sigma squared in my earlier notation. And it then says, well, we test that. We have a chi-squared test with 2 degrees of freedom because we're setting these two variance components to 0. And the test statistic is 36.90. The p-value is 0. What does that mean? We have to reject the null hypothesis that there is no more clustering in the data. And apparently, even though when you look at this variance component for black, it's essentially 0, the variance component on the intercept is still so large that apparently saying, well, that's indistinguishable from 0 is just violating something in the data. That's too big of a difference from 0 empirically to say we can set both of these variance components to 0. Now, here's a little point that I want to pay attention to. It says the likelihood ratio test is conservative, and that's true. Because actually, when you are testing just variances, it gets a little bit different when you also test covariances. When you just test variances, the deviations of the null from the null hypothesis, the deviations from zero, can only go in one direction. You can only get positive values on the variance. And so actually we need to conduct a one-tail test. How do you do that? Just divide this p-value by 2. Half it. Now of course half of 0 is still 0, so that doesn't alter anything to our assessment here, but that's, I think, something that is, that's why they call this conservative. And why do they compute it this way? Well, because it's a general test procedure, and when you have a covariance component, you're also testing at the same time. That, of course, can deviate from 0 in both directions. That can be positive or it can be negative. And so then it sort of says, okay, let's treat everything as if it is two-sided and then compute the p-value. So that's what I actually also have on this slide, which says we should have the p-value. So it doesn't do this. That's why the test is conservative. So in our model, we included race of the respondent, and at one point decided to let it have a random slope. Do we need that added complexity? Well, when we add the variance component, we get this log likelihood with -2 times that being this deviance. When we exclude the variance component, we obtain this log likelihood with that deviance, and then you can perform the test. This, of course, means you have to do it by hand. There's another way to do this, and it's the following way. We've already estimated the full model that has variance components for both the intercept and the slope. And now I'm going to store these estimates. And I do that using an eststo, or estimate store command, and give it a name, say full. And now it's storing this stuff. Now I'm going back, and I'm going to estimate the same model, but I'm removing the random effect on the slope. And I should get on Skype before my father tries to came online. So I estimated this now. So I do the whole thing again, but now I just have the variance on the intercept left. And now I do ELECDEM test, which is the command for likelihood ratio test, and I do full. In this case, we get actually, we get this test. This is basically the p-value. So we can basically get rid of the random slope. You'll notice something a little weird. It's a negative value of chi squared. That's because actually this estimate in a full model of the variance component is so tiny that actually Stata's having a problem. That's what it actually is complaining about. But that's how you would carry out test. What I have in the slides here is not for this model that has the interaction between percent black and black. It just has the random effect for black.
How can you, I mean, if you remove the random slope, it means that all the slopes are supposed to be the same per slope.
Yeah.
How can you have a cross-level interaction? I mean, how can you have an effect of a level 2 on the variation of level 1?
Well, what you're saying is, after you've included that cross-level interaction, there's no more variance left to explore. That's what it means. So, in a sense, you could imagine that you can add, if you add the right level 1, if you add the right level 2 predictors for the intercept and the slope, you could imagine that that explains perfectly the variation that exists across the contexts. In which case, there is nothing left to explain. The variance component goes to 0, and effectively then means that once you have done that, the observations are conditionally independent. That is, knowing their value on the level 2 covariance, there no longer is residual correlation between the observations. So that's what it then means. Now here come some cautionary remarks. Always make sure that the same number of cases is involved in MU and MR. Now, when you do the LR test command, you will actually get a warning if that's not true. But if you do it by hand, you will actually potentially run into trouble. And you can imagine this happening when you, for example, go from a model that contains no level 2 predictors to a model that contains level 2 predictors, but you have missing values on the level 2 predictors, that your sample size starts to fluctuate. Then you should make sure that in the model without the level 2 predictors, you're already kicking out those cases that are missing on the level 2 covariant, simply so that you could compare the deviances. With restricted maximum likelihood, the deviance test on the variance component is only valid if the fixed portion of the model remains identical. This is why I think you have to be very careful using that. Because the estimates of the variance components under restricted maximum likelihood are extremely sensitive to how many fixed effects you're also estimating. So if, in addition to including a variance component, or not including it, you also change the number of predictors in the model, you cannot test anything. There's some special situations that could occur in some really specialized survey situations where the likelihood function that you obtain using Stata is what is known as quasi-likelihood function. Quasi-likelihood functions are not really likelihood functions. They're sort of approximations of the likelihood. Then you should not do a likelihood ratio test. Stata is usually pretty smart about that and then switches to something else. But it could be, for example, Stata allows you to do this, that you have, that you, in addition to estimating this model using multi-level analysis, include robust standard errors or cluster-corrected standard errors. Then Stata will switch to a MALT test. And that is something to keep in mind. It happens because the likelihood is a quasi-likelihood. Before I get to the caveats, I want to talk a little bit about the R squared. Just because I alluded to it earlier, and so now I should delete. The intuition of the R squared in multi-level analysis is sort of similar to the intuition in regression. That is, you have a model that has no predictors in it, and you have a model that has predictors in it, and if the predictors do anything, then the error variance should reduce. And so you can look at the proportional reduction in error. That's your R squared. What is different in multi-level analysis is that you actually can compute many different R squares. You can actually compute an R squared at level 1, that is, start with a random effects ANOVA, then add some level 1 predictors and see what happens to the level 1 variance. Or you could do it at level 2. You could say, well, these level 2 covariates that I'm adding, how much do they really explain in terms of the variation in intercepts or the variation in slopes? And I want to just briefly show you how to calculate that. So I have to specify the model a little bit differently. I'm going to do this going from a model that has no random, that has just a random intercept, to a model that tries to account for variation in the intercept by way of percent black. And since I have missing data on percent black, what I'm doing here is making sure that the sample that I use for this random intercept model is going to be the same as the sample I will use next once I introduce percent black as a predictor. So this is a random intercept model I just estimated with a variance component here. That is, say, I'll give it a take, 40.4. That's the variance component without the level 2 explanatory variable. Now what I'm going to do is add this level 2 explanatory variable. So I'm adding percent black to the equation here. And the model that corresponds to, so this model that I have here is basically saying beta 0j is gamma 0, 0 plus delta 0j. And now I'm going to a model that says beta 0j equals gamma 0, 0 plus gamma 0, 1 zj plus delta 0j. That's the difference. This is this percent black that I'm adding. And if that has any explanatory power, what should happen to the estimate of the variance of delta 0? Should it go down, up, stay the same. It can't go up, because that would mean that somehow we would explain less with an explanatory variable in the model than without. But it could stay the same. If percent black is irrelevant, it could stay the same. If percent black is actually highly relevant, then the variance component should come down. So let's see what it does. So same model, and now I have percent black as a predictor in there, but now we look at the variance component, I call that 26. So what is the proportional reduction in the variance component? 40.4 minus 26 divided by 40.4. And since I'm terrible at arithmetic, I'm not going to try to do this. I'm going to invoke stata as a calculator. If you do DI, which stands for display, everything that comes after is just like a pocket calculator. So what do I have? I have 40.4 minus 26 divided by 40.4. And that's my R squared, call that 0.36. This is the percentage of variance in the random intercept that I've explained by including the percentage of black as a predictor. This is, I think, fairly useful. I'm generally not a big fan of R squares, because I sometimes think people get desperate for the wrong reasons when there are squares in models. The good news is these R squares tend to generally look better than the normal R squares. But I mean, they also convey some real information about how much you've actually explained by introducing the level 2 covariance. So that's how you do that. I don't think there's any automated procedure in stata. You have to do this by hand. It's not that difficult to do. Just make sure that the only thing that changes from the one model to the next is the inclusion of this z. Because if other things change, that R square is going to pick that up as well. So you have to basically just change one thing at a time, and it has to be at the appropriate level. So when I want to look at the R square at level 1, then it's more an issue of what happens to the sigma squared when I have a model without level 1 covariance versus a model with level 1 covariance. That's sort of the standard R squared. This is really about the second level. All right. Then on to some things that in some ways are very troublesome. And unfortunately things we have to think about. Caveats. There are three important considerations when you do multi-level analysis: theory, sample, and measurement. And unfortunately, here is where we often run into trouble. Theory, well, I already mentioned earlier that we cannot really take a empiricist approach to the specification. We have to have theory. And theory demands here are steep because we need to know the selection levels. How many? What are they? That's sometimes something that we can sort of make it empirical matter. If we sort of look at the sampling design, we can say, okay, the levels are given to us. But more often than not, this is something that we have to think about theoretically. What are the important sources of variation? I mean, in electoral research, it's probably always the individual to some extent. Well, what's then next? Is it the nation? Is it the state? I could also have done the analysis I had before at the county level or the congressional district level. I mean, is that a more appropriate level of analysis? The specification of the level 1 model, which is what we also would have to get right when we do regression analysis, but also the specification of the level 2 model we have to get right, including the level 2 covariance selection. So that's pretty steep. And really what we need is to think about micro and macro linkages. And it's not impossible to do that, because I think we have theory there. We have ideas about how context influences behavior at the individual level. It's just that we have to take this fairly seriously, because if we make bad decisions, we can have invalid influences. And here's just one example that I'm aware of. There's a simulation study by Daniel Bauer that shows that if you have nonlinear effects of predictors at level 1, what you fail to do to consider that, and you say they're all linear, you can get false readings of having varying slopes. Because what's happening is you have basically a poorly specified model at level 1, and what the multi-level variance components are doing is trying to rectify that. They're picking up the fact that you have misspecified your first level. So that is one piece of advice. This takes theory very seriously. There's not much of a piece of advice, because I mean, if I could tell you what the correct model of electoral behavior is, then I would probably be advising political parties instead of teaching this class today. But I mean, nobody knows, of course. I mean, we have to it's a work in progress. It's all, we never can be entirely certain we have the right model. It's just a call that you have to take the specification very seriously. The other couple of points I want to make there is actually some more specific advice I can give, although I fear is advice in the direction of attend more classes to learn some new things. Sample size requirements. In multi-level analysis, I've already mentioned this, the cluster size is less relevant than the number of clusters. And ideally, the number of clusters should be large. As I said, some people say at least 50, some people say at least 100. I always find it a little bit weird to cite these numbers, because I think it's really situation dependent. But there are some simulation studies that show that if we have a small number of clusters, we can have serious bias in at least the variance components, but potentially also the fixed effects. We also have low statistical power, and probably often have in electoral research is, well, we have lots of observations, but not many contexts. What to do? Well, at least there is one suggestion in the literature that says you should become a Bayesian. And Bayesians, there's a lot of reasons why you should become a Bayesian. Well, there are lots of reasons why you should become a Bayesian. But Bayesians actually can demonstrate this in lots of instances, that you can actually get rid of small sample bias even with uninformed priors. It's no wonder if you sort of tell it, this is what reality is, that it will do is it will get you something because it won't look much at the data. That's not very persuasive. If you say, well, I sort of know what reality is, but the variance around my prior guess runs from negative infinity to positive infinity. That you then can get something out of the prior is perhaps more surprising, but you can't. This is also true. More generally, people have shown that if you have the right uninformed priors, you can actually get rid of small sample bias in maximum likelihood estimates. So this really is, I think, one way to go with this. But again, it requires you taking a different class. I'm sad to hear that this is your last workshop. Because I could have done that. The other thing that Bayesians can help us deal with is a problem that you mentioned earlier. This is a slide I just added. It's not in your package yet. Because I'd be sort of saying, well, level 2 units are sampled randomly. Well, are they really? I mean, in a sense, it was true the example I showed. But if you look at the 27 member states of the European Union, it's not even a sample, let alone a random sample. Now, is that problematic? It depends on one's perspective. And here comes again the difference between frequentists and Bayesians. Frequentists say this is a big deal. Because to frequentists, the only source of variation is sampling variation. And if you have a population, you don't have a sample, so you don't have variation. And I mean, I know that people run into this difficulty because I once had a PhD student who presented a multi-level analysis with countries as the unit, as the level 2 unit at Nuffield College, and the statistician there, Dave Cox, looked at it and said, I believe this because we only have a random sample of countries. And Bayesians, well, they're okay much. Because to Bayesians, the source of variance is not necessarily sampling or only sampling for sure. Variance in the Bayesian sense is just our uncertainty about reality. We just don't know what these parameters are. We can try to learn about them. Hopefully, over time, we will get more precise insights about them. But there is always going to be variance. And it doesn't matter whether I study the population or a sample. It's just my inherent uncertainty. So, is this a big deal? I mean, I myself have often done this with countries and have so far been able to get away with it. And I think there is a good justification coming out of this Bayesian framework, although it would suggest that you really should estimate this in a Bayesian way. Then the last point I want to make, which I think is very important too, is we need to really seriously think about our measures, in particular our measures of the dependent variable. And I think this is starting to become something that people in political science are sensitive to, but I don't think we're sensitive enough yet. What we want to establish is that our measurement instrument really behaves the same way in the different level 2 units that we're studying. We need to have measurement equivalence. Without that equivalence, it's actually possible again to get false readings of random variation in the intercepts and slopes. And what we actually need is a particular version of measurement invariance, which is actually one of the strictest versions, namely scalar invariance. We need items that measure the same thing in different contexts, that have identical metrics across the context, and that don't have differential biases across the contexts.
I know Eldad and Peter Schmidt have been hammering this issue home, but isn't the sad thing about this is that we rarely get metric invariance and we practically never get scalar invariance?
Yes, it's well, the even sadder thing is we're very frequently not in the position to actually even assess it. Because one way to avoid the issue is you basically have one measure for the construct, then you can test for measurement equivalence, and so then, but it is an issue, and I will show you why in a moment, because it really can mess up results. So here is just a little bit, so this is a factor analytic model. So here is my measure for individual I in context J, and then here is the underlying latent variable that I'm trying to measure, eta ij. Epsilon here is measurement error, and then I have factor loadings lambda j that specify the metric, and tau j's that sort of specify the means. And we want under scalar invariance to be the factor loadings to be the same everywhere, and the taus to be the same everywhere. Now what happens if that's not the case? Well, here's an example. I have a model here, which is a hierarchical linear model stated at the level of the latent variable. So eta ij is equal to gamma 0, 0 plus gamma 1, 0 xij plus zeta ij, where that is unexplained variance in the eta. Notice I have no random variation in intercept or the slope. Now, I have a measurement model that links the observed thing that I'm actually able to analyze to this latent variable, which is unobserved. Now, this yij is equal to tau j plus lambda j, eta ij plus epsilon ij, and notice the subscripts j on the tau and the lambda. Basically, that's saying there is no measurement invariance. Now, substitute this equation into that equation, then you get yij plus tau j plus lambda j gamma 0, 0 plus gamma lambda j gamma 1, 0 xij, and then this error term. What's important to notice here is that this tau j plus gamma j plus lambda j gamma 0, 0 now varies in j, and this slope lambda j gamma 1, 0 xij also varies in j. And if you don't pay attention, since we can't estimate all of these terms, they're sort of rolled into one estimate of the intercept and one estimate of the slope, you will get an intercept and a slope that vary. But they don't vary because there's really a varying effect of x. No, they vary because there's variation in how we measure across different contexts. It's sort of a trivial point, but I think one that we really should take serious. Even though you're right, it is not so easy to get measurement invariance. Are there questions about this hierarchical linear modeling stuff? These last comments are not to tell you never do this. These last comments are really to say, well, look, be aware of some of these issues. But actually, even if you were to just do a regression analysis, you still have the problem of measurement invariance to worry about. So,
can do, or you should do Bayesian modeling if assumptions are not met in the multi-level model. So all kinds of assumptions that we have in the regression, is that correct?
Well, sort of, yeah, but it's sort of paradoxical because what do you do when you do Bayesian? You actually add a bunch more assumptions because you have to end up specifying prior distributions, which are additional assumptions. So I'm not entirely sold on that point because you can get those wrong too. But it is true that you can circumvent certain things more easily when you do a Bayesian. So, like, if it's really the case that there is sort of measurement error, it's fairly easy to build that into the Bayesian setup, for example. I mean, Bayesian stuff, I mean, I believe in it deeply, but it also has some drawbacks. And not the least of which is very complex.
When we do the R squared for if we get a level 2 variable, can we do something similar if I just want to see level 1 variable, if I get it to other level 1s? If
Yeah.
there is a difference.
Yeah,
Because you said it's
you do it with the sigma squared rather than with the tau. Yeah, it works exactly the same. So you start there with a random effects ANOVA, so no level 1 predictors, and you look at the sigma squared, and then you would add the level 1 predictors, again making sure that the sample doesn't change from one to the next analysis. Look at what's happened to the sigma squared, and then you can come up with a proportional reduction in error. That would be your level 1 R squared.
One more. I didn't really understand what's the difference between adding covariance, independent covariance, and structure.
So the difference is if you look at this variance covariance matrix of the level 2 errors. Oops. So this thing that we saw earlier. What I've depicted here is unstructured. And when you do independence, instead of this tau 0, 1, you assume that to be 0. That's independence. So that's all that's the only difference here. And the reason why that is actually useful is that even though there's often no reason to constrain this to 0 a priori, it's usually if you have problems with estimates in that matrix, it's usually with the covariance terms and not with the variance terms.
When discussing this R squared, so the variance term has a certain uncertainty on it, right?
Yeah.
It had, I think in the second model, it was 26 point estimate, but the upper bound was 58 or so. And we compared that basically to something that we had in the previous model, which was, let's say, for the lower bound of 20 something. So I was just wondering whether this sort of overlap in the sense of the uncertainty measures that are on the variance component should have any sort of influence on how reliable this
Yeah, it's
difference
It's
as is.
completely ignored in R squared. And it's notoriously difficult to get a good sampling distribution for R squareds. So that would be one reason to be a little bit careful with these things. In that case, if you're worried about that, I would just say here, is the variance component with a model that, that includes the level 2 covariant. Here's the confidence interval on that, and here's the variance component without that, and then here's the confidence interval. Because there's no good way of bringing that uncertainty into the R squared measure in this field.
Because somebody could actually argue that it's not necessarily better.
Yeah,
I mean,
that's
or at least in 40% of the.
Yeah. Again, this is one of these places where actually the Bayesian world is a little easier. Because you could actually get a posterior on the R squared that would get really the measure of uncertainty. So, before I move on, maybe we just ought to take a break first before I move on, but just to recap. So there are reasons why we do this, and the reasons are that we want to get insight. We also want to avoid some statistical problems, like clustering, messing up the standard errors. What I like to do as sort of a modeling strategy, but I'm just, there's no law that says you have to do it this way. But I always like to start with this random effects ANOVA, just to get a feel for, okay, what portion of the variance is at level 2, what portion is at level 1. And then I typically continue by adding the covariance at the level 1. And then what I tend to do, because that's sort of the minimum specification, is to then allow the intercept to vary. But if you have good theory, and I think often we do, then you may also want to let the slope vary. I mean, these are sort of a couple of examples. You could say, we know there's, for example, when you look at attitudes towards European integration, there seems to be a gender gap. Women seem to be more negative than men. Well, this gender gap, that effect of gender, maybe we can, it's not the same everywhere. And maybe we actually have sort of good reasons to speculate how it goes. Because you can imagine that if you are, say, a woman in a Scandinavian country where the position of women is generally quite good, you look at the European Union as a race to the bottom. That is, you have a very good situation, but everything is going to go pushed to the lowest common denominator, and that makes you worse off. So maybe the effect of gender is bigger in that kind of country. So think about, there is often theory to tell you, like, there are these effects and even explanations of variant slopes. In this case, for example, the generosity of the welfare state could be such a predictor. What you want to make sure of then is that you actually specify the model accordingly. And then I would start first by just specifying a random intercept and slope, and then add an explanation for the variation in the intercept and the slope. And then, when you have added this explanation for the slope in particular, but also for the intercept, don't just focus on the fixed effects, because sure, that's interesting, But there's so much more you can do with this multi-level analysis. You can look at these empirical base estimates, and they can give you pretty nice insight in what happens in particular countries. And they may have sort of a diagnostic purpose too. Especially if you're thinking about sort of mixed method research. You could look at these empirical base residuals or empirical base estimates and find out that there is a complete outlier that doesn't seem to behave at all like any of the other cases. Well, maybe that is a worthwhile case to actually investigate more in depth through qualitative analysis. Sometimes we may also point to a failing assumption where you said, well, it's all nicely normally distributed and there's this one point that messes it up. But, I mean, there are lots of things that you can do in interpretation that can also guide you in sort of subsequent research. So, that's one thing. I think you should really look at these random effects in addition to the fixed effects. That's one of the great benefits of doing multi-level analysis. And then I would also say, use graphs as much as you can. Simple slopes, depict them graphically, because it is much easier to then talk about them than to try to explain in words what's going on. So, and this use of graphs becomes even more important once we get to nonlinear models, which is where we will be headed next. But I think if there are no other questions, it's probably good to have a break. And then